Here's another look at xylem vulnerability curves, and recall that xylem vulnerability curves show the degree to which conductivity is lost as water potentials becomes more negative. And that's due to accumulation of cavitations or embolisms in xylem. So that at 100% loss of conductivity, the xylem is completely blocked by air-filled conduits. Like most physiological data presentations, especially with water potential, because water potential is negative units, you see variation in how people present these. So in this case, we have water potential presented in absolute units, going from less negative to more negative water potentials. And here, this is a presentation of xylem vulnerability curves for 4 different species. And in this case, we're seeing species that are more typical of mesic habitats or moist habitats, box elder and birch, and then sagebrush and ceanothus are not even trees, they're desert shrubs. Okay? And of course you see variation in what their curves look like and in their vulnerability to cavitation. So remember, one parameter we can use to describe vulnerability to cavitation is psi 50. So recall psi 50 is just the water potential at which a particular species or curve has achieved 50% loss of conductivity. So for ceanothus in this curve, psi 50 is negative 9 megapascals. Okay, so that's the characteristic of that curve. So what we can see is that the more mesic species are more vulnerable to cavitation, and then the desert or xeric species are more resistant to cavitation. Now, I'll talk in more detail later about the relationship between vulnerability to cavitation and stomatal closure, but suffice it to say at this point that more resistant xylem, in other words, xylem that's more resistant to cavitation, enables stomata to remain open at more negative water potentials. And of course, you can see how that would be adaptive for ceanothus and sagebrush to have stomata that remain open at more negative water potentials. And basically more resistant xylem enables that to happen. And we'll go into that in more detail in a little bit. Okay, here's another presentation of xylem vulnerability curves, but in this case, we're looking at variation between root and branch vulnerability to cavitation in loblolly pines. So we're looking within a species at how vulnerable different organs are to cavitation. And again, we're seeing variation in how people present this. So in this case, the y-axis is backwards or reversed relative to what we have typically seen, where this shows percent of maximum conductivity. So this is 100% conductivity, and as we go down on this axis, that's loss of conductivity. Okay, so in this case, when we go towards more negative water potentials, the loss of conductivity is shown by a reduction in the y-axis. So basically, we've flipped the y-axis and also flipped the x-axis relative to the last graph we've looked at. So you have to do some mental gymnastics in interpreting some of these curves. But the interesting thing here is you can see that there's fairly large variation in vulnerability to cavitation between branch tissue and root tissue. So let's look at psi 50, and psi 50 works the same regardless of how this is presented, fortunately. So psi 50 for branches is what? About negative 3.5 megapascals. And then for roots, we'll just sort of take the average. Let's do a different color. Psi 50 for roots is maybe minus 1.25. So what this is showing is that roots are more vulnerable to cavitation than branches. And this is an early paper. It makes me feel old. This paper is it's about 23 years old. And I remember when this paper came out. But this has held up in the literature in that roots are very often shown to have a less negative psi 50 than either stems or branches. So this is held up, and there's some speculation in the literature about why that may be. In some cases, it's just consistent with the water potentials that tend to be encountered by that particular organ. Branches tend to encounter more negative water potentials than roots do, and therefore it's adaptive for them to be more resistant to cavitation. But there's also some other hypotheses out there, and you can see that when you read the papers. But at any rate, there is variation in vulnerability to cavitation within plants. And I think there's actually a movement in the literature to do a better job of characterizing hydraulic architecture of roots, because sometimes roots are a pain to measure almost any physiological characteristics, so we need more data on the hydraulics of roots. Up to this point, when I've been talking about cavitation and embolism and vulnerability to cavitation, I've been referring to drought-induced cavitation. Cavitation that's induced due to reductions in water potential in the xylem that enables air seeding to occur across a pit membrane. So that's drought-induced cavitation. But there's another kind of cavitation that's called freeze-thaw cavitation. And that's cavitation, you can probably jump to the conclusion here, that occurs after a freeze-thaw cycle that the xylem has gone through. And the ultimate effect is the same as drought-induced cavitation, in that freeze-thaw cavitation also results in a liquid water-filled conduit becoming embolized or filled with air and being blocked. But the mechanism is different. Mechanism is different than drought-induced. Okay. And the morphological determinant of risk is different. Okay. So in freeze-thaw cavitation, the mechanism is, okay, you've got a tree in a cold climate and it freezes, and the liquid water in the xylem freezes. When that happens, there is a little bit of air dissolved in the liquid water. Not much. Remember I said there's no air in the xylem. Well, I lied to you a little bit. There's just a little bit of air dissolved in the xylem. But typically it's not meaningful. But when that xylem freezes Any air that's in solution comes out of solution and forms a bubble. That's why I've got a picture of ice cubes on the slide here, because we're all familiar with ice cubes from our freezer and the fact that they're not clear. And we know that the water that we used to make the ice cubes was generally clear. We could see through it. But when frozen, those ice cubes are cloudy. And that's because when we freeze that water, that liquid water, there's air in solution, and that air comes out of solution when it freezes and forms bubbles. And you can actually see some of the bubbles here on the edge. You can see little bubbles there, but all that cloudiness in those ice cubes is air bubbles. Now, when xylem freezes, it's probably not cloudy because there's very little air in solution, but there may be, 1 or 2 bubbles in a vessel element or in a tracheid. And when that xylem then thaws, some of those air bubbles may go back into solution and become dissolved, but some of them may remain a bubble when that phase change from solid to liquid occurs. And if there's an air bubble that remains a bubble, when that xylem, when the tree then starts transpiring and that xylem starts going into negative water potentials again, that air bubble will expand and fill the tracheid or vessel element and cavitate it. Okay, so that is the mechanism of freeze-thaw cavitation, is air bubbles coming out of solution and then expanding when the tree starts transpiring after thaw. Okay, so the mechanism is different than drought-induced cavitation. It still involves air bubbles that nucleate that cavitation, but the air bubbles appear in the conduit in a different way. So I haven't mentioned a pit membrane, so the mechanism is different in this case as well. So I'm sorry, the mechanism is different, and therefore the morphological determinant of risk is different. So for freeze-thaw cavitation, the morphological determinant of risk is conduit volume. Okay, larger conduits are more vulnerable to freeze-thaw cavitation. So that is, the opposite of what I told you for drought-induced cavitation, where I said, for whatever reason, it is intuitive that larger vessels are more vulnerable to drought-induced cavitation. That really hasn't held up in the literature. For freeze-thaw cavitation, that is true. Larger conduits are more vulnerable to freeze-thaw cavitation. So the data shows that, where this shows on the y-axis, this is the percent loss of conductivity. So PLC FT equals percent loss of conductivity due to freeze-thaw. Okay, neat abbreviation there, PLCFT, where obviously 100% is a greater loss of conductivity versus conduit size. So larger diameter conduits going to the right, where these values down here are probably tracheids, and these values out here are vessel elements. And there's overlap between them. So this tells us a couple things. One, larger conduits are more vulnerable to freeze-thaw cavitation, which tells us that perhaps, or that tracheids in general are more resistant to freeze-thaw cavitation. And there's actually some folks, interpret this relative to species distributions. So if we think of, for instance, the distribution of conifers versus angiosperms, we tend to see that conifers tend to be distributed in more northern latitudes. So for instance, this shows the distribution of the boreal forest. Okay, boreal forest has abundant conifers. Now there are angiosperms that live up here, but in general boreal forest is conifers, and you see a greater abundance of conifers or gymnosperms with tracheids as you go further north. So when you look at ecological factors, I always preach that it's never one thing. So I will guarantee you that it's not just vulnerability to cavitation that influences the distribution of conifers across the globe. But I think it's likely that the greater resistance to freeze-thaw cavitation of small tracheids or small volume tracheids is probably one factor that explains that distribution. Here's another example of a distribution. This is the distribution of palms in the United States, and palms do not occur very far north. Palms are very vulnerable to freezing, and one of the likely explanations for this restricted distribution and the vulnerability of palms to freezing is that palms are monocots. Okay, so remember that palms are monocots. We know that. What's one of the characteristics of monocots? They have no secondary growth, and another way to think about that is they do not produce new vessels each year. One, they have vessel elements. They're an angiosperm. Okay, so they have larger conduits. They're more vulnerable to freeze-thaw cavitation. But so do oaks and elms, and they live in places that freeze. But oaks and elms are dicots, and they produce new xylem every year. So they can replace cavitated vessels after the winter by growing new vessels. And a lot of those dicot angiosperms are also deciduous, so they just don't transpire during the winter. Palms tend to be evergreen, and they cannot produce new vessels in the spring to reduce or to replace cavitated vessels. So I think all of those things combined mean that vulnerability to freeze-thaw cavitation is probably an important factor that influences the distribution of palms. Probably more important than that influence on the distribution of conifers, I would guess. One question that may have arisen in your mind at this point is when a conduit, a vessel element, or a tracheid embolizes, cavitates, and is filled with air, does it ever refill, or is that a permanent alteration to the hydraulics of the tree? The short answer is probably. There's quite a bit of observations in the literature of refilling conduits, and one way that manifests is, for instance, people might be diurnally during a day, for instance, measuring hydraulic conductivity of branches on a tree, and maybe they see high hydraulic conductivity on branches in the morning, but then in the afternoon they see low hydraulic conductivity, but in the late afternoon or evening they see hydraulic conductivity go back up. So if those embolisms were irreversible, we wouldn't expect to see an increase in hydraulic conductivity throughout the day, or even from day to day, for instance. But there have been observations like that in the literature. So there's a fair amount of evidence that hydraulic conductivity can increase, which would infer that embolized conduits refill. Probably the bigger question is, if they do refill, how? What is the mechanism for that? And if you think about it for a little bit, that's actually pretty tricky. It's a tricky question because let's imagine we have a vessel here filled with air and the vessel next to it filled with liquid water. Okay, this is at a pressure, let's say it's psi, is plus, so we'll call it psi p, is plus 0.1 megapascal. That's atmospheric pressure. And then this vessel, generally its psi p equals negative, some negative megapascals. So which direction is the pressure gradient? The pressure gradient is in this direction. Even if transpiration stops at night, this liquid-filled conduit will still at least be in equilibrium with the soil, which is still some negative water potential. So it's hard to imagine under most conditions a situation where water could move in this direction. It's hard to imagine that situation. So there's a couple of situations where maybe that could happen. So root pressure is one possibility. Root pressure is just when there is, at night, often due to osmotic potential in soil, the water potential gradient allows passive movement of water into the roots. That pressurizes the root system. So that causes psi in xylem to be positive. That's called root pressure. So this occurs. It's not, impossible or uncommon. So for instance, when you see guttation in leaves, little droplets of water being exuded often from herbaceous plants, that's due to root pressure. And there have been situations where this has been observed in trees. Osmotic movement of water into roots, and that pressurizes the xylem. So that's one situation where this could potentially happen. But it happens at night. This can't happen when the tree is transpiring. So then that's the bigger question, is what might be the mechanisms for refilling when tree is transpiring and psi in the xylem is negative. So what might be the mechanisms for that? That's the bigger question. The take-home message regarding refilling embolized vessel elements or tracheids while the liquid water part of the xylem is at negative pressures is that it will require some kind of active mechanism. Essentially, there needs to be some kind of pumping. So Missy Holbrook and her lab in the late 90s published a paper sort of outlining what would be necessary for this to happen. And essentially, it needs to involve living cells in the xylem. So those would likely be parenchyma cells associated with ray files. Would need to pressurize water and pump it into embolized vessels. So this is a diagram showing basically the movement, the pumping of water from ray cells into the xylem and the reabsorption of gases into liquid water, and then the diffusion of gases into adjacent cells. And all of that would be required to refill embolized conduits. There is some good evidence that, like I said, there's evidence that refilling happens, and there's evidence that it requires active energy. So this is one example in the literature. These data show recovery from embolism. So this is percent loss of conductivity on the y-axis. So they're starting, the first bar in each group is 2 minutes. So they're starting with branch segments that are about 40, have lost about 40% of their conductivity. And they're showing recovery of conductivity like this. So the bars going down show recovery of KH. And then they have 3 treatments. This essentially is a control. So this is basically KCl. That's a solution that's usually used in measurements of hydraulic conductivity. This is basically an ATP enhancer. So this is a situation where there's more energy available in these chutes. And what you can see is that the recovery is faster and more extreme when they enhance basically energy availability. This treatment in the middle is basically an ATP inhibitor. So this is less energy available in the chute. And you can see that recovery is inhibited in that situation. So this is, evidence that recovery of hydraulic conductivity is dependent on the availability of energy from living cells in those chutes. These data show something similar. And these basically show 2 measures of embolism recovery on the y-axis for some period of soak time. So 2, 4, and 6 hours of soaking. And then they show what happens, basically how recovery goes in the light or in the dark. And what you can see is that in the light, you get significant recovery from embolism, whereas in the dark, you get almost no recovery. So this shows, again, that availability of photosynthate, for instance, is necessary for recovering from embolism. And when we look at the structure of xylem and think about, okay, if living cells are necessary to refill cavitated vessels, for instance, there should be living cells associated with all or most vessels. And when we look at cross sections of wood, so for instance, these are examples of, in this case, this is an oak cross section. This is a cross section of sugar maple. In all these cases, we see, okay, these are vessels right here, right? And if we look closely at every vessel in this cross section, there is a ray that touches it. Same here. When we look at these vessels in this diffuse porous wood, there's always a ray a file of ray cells either touching or very close to that vessel element. And when I look at, for instance, cross sections of gymnosperm wood with tracheids, while in any particular cross section there's not necessarily a visible ray touching every particular tracheid, we need to remember that in those in the case of those cells, tracheids tend to be very long. So likely, even if in any particular cross section we don't see a ray cell touching a tracheid, it's likely that if we went above or below that particular cross section, because those tracheids are so long, there's likely some point at which that tracheid encounters a ray cell. So there's also good support from the anatomical literature and images that likely living cells are there and available to assist in refilling cavitated conduits. So there's some good circumstantial evidence there. So all of that being said, the current state of the literature, so if you look at some recent reviews that are cited in your notes, this is up in the air to some extent. There are some recent publications that suggest that the evidence for refilling, so increases in hydraulic conductivity during the day, in a lot of cases may be artifacts, so artifacts of measurement, and that the evidence for refilling is not as solid as we thought it was. So I would call this another situation in the literature that is still an open question. It's intriguing, but it's still an open question, which means there's lots of room for research, which is exciting. So keep an eye on that literature. This is one of those ongoing and open debates in the literature for tree-water relations.